Hi everyone, we are going to listen to Ben and Vlada, and they are going to talk about infotainment system hacking.
Hi, hello everybody. So we will start with our presentation. So thank you all for coming. It's always a pleasure to be in Serbia, in my home country, and to be able to present something that we are doing. So today we are going to talk about one of the very interesting and very hot topics today, and that is about automotive security, and specifically we are going to discuss stuff about infotainment systems, which are part of most of the cars today, and what are the dangers and what can you do to check security and to ensure that your car is under your control, not controlled by somebody else. So a little bit about us. This is my colleague Ben. Wave.
Hello.
Yeah, he's from France, as you see, so he's not perfect, of course. He's not. So he likes Java, but if you recall, we were here two years ago, and his notes say just Java lover. Now I managed to make him love Python also. So I see that as my great accomplishment in developing my friend. And my name is Vladan, and I'm a monster. I'm scaring people around the world and living off their screams. So one important announcement. So no cars have been hurt during preparation for this presentation, mostly. So a little bit wires around stuff, but car was safely and soundly returned back to his proud owner. So big question is, what is infotainment system actually? So if you have car and then you sit in front seat, you see infotainment system, or at least part of it. That part is interface to you. So we will go into details what it is, but what is the problem with it? Why it is a problem? So you know our favorite car, Yugo, which is manufactured here in Serbia, doesn't have any security problems. Brakes might work, might not work, but that's not a problem. We used to deal with that. And heaters are nice. If you push it to start during the winter, it hits your hands, so you're not cold. But other cars, which have a little bit more sophistication added to it, are a little bit more complex and has a little bit more problems associated with this complexity. So as you can see, this is my favorite slide. It shows how cars are actually complex. So this is number of lines of code that is used into different computers across the system. So we see that Facebook has roughly slightly less than 7 million lines of code. Boeing 787 is around that same number. Ford is at 10 millions. Office has 50 millions. But modern car like Ford F-150 has 150 millions of lines of code. So it's huge amount of code that goes into development, and this is code that is run on different computers in a normal car. In a standard car, there can be about 200 kilograms of different wires and computers. So we have around more than 100 different processing units. So I'm not saying full ECUs, because not all of them are full ECUs, but there are small computers which are dedicated to just simple function, or they are more complex, like ECU that controls your engine, or chassis computer that controls your cabin and everything inside it. So as I mentioned, what is actually car entertainment system? So it is the screen that interface with you. So it is usually, you see it as a stereo or FM radio or navigational device that is in front of you, but in modern cars it can serve a little bit more than just this simple information that we used to. So today we practically have a concept that our cars are like our phones on the wheel. So you can drive your computer around, and with newer cars like Tesla, you have autopilot, which can do a lot of stuff for replacing the driver. So the driver is just there to control that something doesn't go wrong, but car can take over a lot of functions. So it is not just cruise control that most of us has, but they are much more advanced, and there is a concept of autonomous car that enhances this completely, removing the driver as a variable. So you will be just passengers, all passengers in car, there is no driver. car is a robot that know how to go from point A to point B. Of course, it will be interesting in our roads. I always want to see how it will actually work in Serbia. So when we have detours, we have signs, and even humans cannot decode what they actually mean. But okay. So important part, what you see is just front end of this interface. So there are a lot of systems that run behind the wheels. So it has a navigation system, cameras, it can offer browsers, connection to internet, car statistics. You can use it to interact with mobile applications, to do remote unlocking of your car. So car can send you different information, so it can be tied to tire pressure sensors. So there is a lot of information flowing around the car in order to make your drive more enjoyable and more safe. But does it do that? So as I mentioned, each car has a huge number of systems. So this is a little bit hazy, but I hope you can see it. So this is a typical electrical car, actually. So, but all of them are following the same concept. You have one bus which is exposed to users because it is required by law. Each car that is on the road right now must have implemented OBD interface. So it is a small port that is somewhere under the front part of the car, and diagnostics can be done. So if you take your car to the repair shop, they will connect to this interface and they can read faults, they can see your gas consumption, so they can exchange some information. They can even update ECU computer from this interface. So it is really complex interface, and it exposes few of more standard protocols like CAN bus, K2000. So there are a lot of protocols that are supported by this system, but problem is that modern car just expose this interface via OBD. This is not the systems that are used behind the curtain. So some of cars still use other CAN bus in order to communicate between different computers. As I mentioned, there are a lot of computers in car. So CAN bus can be used for communication between those systems, but it is usually isolated from OBD. And in newer cars, they've completely abandoned concept of CAN bus, and they have some other protocols which can be based on even fiber optic communications, but they have simulators. So they will emulate OBD because it is required by law to have it. So what you can capture from your OBD interface is not full communications that your car is doing. It is just something that car provides as a convenience in order to be able to make some of diagnostic equipment work. So it is not full communication. It is not all messages that are exchanged between your main central ECU, for example, and chassis computer that is used to unlock the car. So it is, as I mentioned, it's complex, and it can contain more than one unit. So first unit is just a note, the images that we are showing are not of the devices that we have been testing. So these are just generic pictures because we cannot show you real pictures of devices that we have tested. So as I mentioned, so every infotainment system can contain of one or more different nodes which communicate between themselves, and they collect all this information from different sensors in the car. So they can track electrical parameters, temperature, humidity, tire pressures, so mass of the vehicle. They can show you which mode, fuel consumption. So problem with this is how you update all this code. So as I mentioned, there is a lot of code going into these systems, and it is not easy to accomplish because usually you cannot do it by yourself. On your standard Windows or Linux laptop, you just connect to internet, retrieve updates, reboot machine if necessary, and you're good to go. You are fully patched, and until next second Tuesday of the month, you are usually safe enough. In car, it cannot be done like that. So you usually need to drive your car to a repair shop and they will do it for you, and you don't do that regularly, and even if you go to car shop, they will not offer to do it for you, so you need to ask them. And in case of problems, usually manufacturers need to do recall of large number of vehicles in order to fix the problem. So it's really complex system and can lead to a lot of problems. Okay, this is magic wand, it can make stuff disappear. You're still here. Okay, it was just a presentation, unfortunately. So, as I mentioned, first and the most exposed part of this system is head unit. It is the thing that is embedded in your dash and which is used for you to interact with the system. So it is usually a large screen with some buttons or touch screen, and you can select different functions and you can watch movies. In good cars, you cannot watch movies while you are driving. So if your speed is over 3 miles per second, we are not driving the space shuttle. So 3 kilometers per hour, it will disable movies, but in some cases we saw it doesn't happen, so you can watch movie while driving. So talk about distracted driving. So it provides some functionalities that are audio amplifiers, car stereo, Bluetooth connectivity, USB support, and it communicates with CAN bus. So usually for OBD side, but sometimes it can be interconnected with other systems on the CAN bus. Why? To provide you some additional features. So you can just select one of these soft buttons and then open your trunk, for example, or you can check your fuel consumption or track your fleet. There are different functionalities that are exposed by head unit, but head unit is just a simple device. Usually we call it just a radio device because its primary purpose is to be AM/FM radio, which is a simple device. And behind the screen, we have usually additional device which can provide additional functionalities, of course. So these extension boxes can contain GPS receiver, advanced FM tuners, Wi-Fi, USB support, so hands-free profiles, so a lot of stuff that can be added. So what we see, the different manufacturers use this box in different manners. So they can have more than one different level of features that they are offering. So simple devices will offer just single screen with basic radio, but as you go up in your car equipment, they will provide additional features like GPS navigation. That will be one device, then they can add another device which will offer something like road assistance, connectivity to other systems, connectivity on the internet. So you will accomplish a lot that you can do from your phone, just from your car. This second device usually communicates with your screen device because it would be weird to have more than one touch screen. So you have 1, 2, 3 touch screens. So they do not like, that is not really user friendly and usable. So if you need to do something, you need to think, oh, on which screen I need now to click. I have 3 of them. So instead, they are interconnected using some proprietary or internal protocols to communicate between each other. And navigation extension box, for example, can take over a screen from the main screen head unit. So it will reuse just the screen, all other functionalities will be provided by the second box. So they are made to work together, and they communicate between each other. So I will later show you why is that important, but they are using some kind of inter-equipment communication protocol, which can be something that is well-known, standardized, or something proprietary. Automotive manufacturers like to have very proprietary stuff for some reason, so they make everybody's life much more fun than it should be. So how these devices look when you open them. So as we are very noisy and we like to disassemble stuff, first thing that we did when we got these boxes is, of course, open them up to see what is inside. And we found these specific line of devices are based on Texas Instruments automotive computing chip, which is optimized to run a QNX operating system. This Texas Instruments is based on ARM v7 processor, so it is similar as older phones. And it has a lot of capabilities built in it. It has GPU for video processing. It have additional peripherals to process network connectivity, USB connectivity. And it is served by some external peripherals like flash memory, FRAM, SD card, flash cards. There are a lot of interfaces which are used for this chip to communicate with peripheral devices which are not integrated inside SOC. So if you go to manufacturer site, you can see that there are a lot of different families, not just by Texas Instruments, by other manufacturers also. So what is interesting here is that everything was fully soldered, so we cannot remove anything without actually the soldering stuff. And there were some interesting pads on PCB which are exposed for us to have fun with them later. What I want to focus at this point is about operating system that is running on these devices. And in these specific cases, and it is very common in automotive world, so they can use Android. We saw they can use Windows CE or Windows 7 embedded, but in this case, the most pervasive on the market is QNX. QNX is an operating system which resembles Linux. It has the same philosophy, but it utilizes a microkernel, and it is originally developed a long time ago, and it become more it gained market presence as BlackBerry devices were using this operating system on it. So all BlackBerry devices are running on QNX, older versions of QNX. New versions of QNX are of course optimized a little bit more since BlackBerry is no longer a platform that has any interesting market presence. So they are now optimizing to support ARM and Intel platforms. And it uses the same concept as Linux for security approach. It supports a lot of other services. We will come to that part. But what is important in this case, device is using QNX, but all the interaction, all GUI is done via Flash. So it was modified version of SWF, similar to BlackBerry, and it uses Lua scripting in behind to drive the features. Of course, it used dbus for communication for internal systems services which run inside the QNX, and it supports Java to ME. It is very old protocol. Of course, I have Java guy here, so he's happy now. This is a weird way to write Python, by the way. Java. So also, QNX supports a lot of different file systems which are not very compatible with stuff that we saw, and they're fairly unsupported by anything else except QNX. So as I mentioned, all the QNX resembles Linux by its features and supported capabilities. It's different because QNX is developed from scratch. It's not developed based on Linux. It's closed source, it has specific kernel, it is really expensive, so developer license for QNX is like $12,000 per seat. So it's not cheap, it's not easy to play with it if you are not company, but you can get, if you go on their site, you can get trial license which is valid for 30 days. So if you want just to see the toolkit and to see how it works, it is good enough. So it uses proprietary file system, as we already mentioned. Most of those systems are mounted read-only because you don't want to suddenly stop your car and to lose the file system on your control unit in your car. That would be a really bad approach. And security is not very mature in these devices because they focus on being closed source and being proprietary. So it's security by obscurity, which works to some extent, but it is not enough. That can be one layer, but it's not enough to be really secure. And what we discovered, it is very difficult to cross-compile for Linux if you don't have this very expensive SDK that you need to buy. So we can go a little bit in boot process. So when you power on your device, so when you give a contact in the car, device will be powered from the battery, and it will start to do initial program loader. Initial program loader is a piece of software that will that acts as any bootloader, so it will actually load the image, where is the basic kernel with the necessary drivers, and then it will boot into full system in the end. And as a last point, it will load overlay flash operating system, and there are some user programs that are deployed on the platform. So as I mentioned, security is not very mature in these devices. So during the exploratory phase that we did, we discovered that first thing, the device is supporting standard Linux user permissions. So you can have different users with different levels, like same Unix, but there is no sandboxing. So all processes share memory the same way as in Linux, so they are a little bit isolated, but if you become root, you can do anything and interact with other processes. It supports some plain text services, including Telnet, which can be enabled or disabled by default. It supports QCon. QCon is QNX proprietary interface for debugging. Big problem with it is that it is not authenticated. So if you have QCon running, you can just simply use QCon client to connect to device via TCP/IP, and you are done. You have full control of the system as a root. Due to performance issues, so you don't want to go into your car, sit down, give contact, and wait for 3 minutes for system to boot. So manufacturer recommends to disable some of security features like verifying integrity of image that is being booted, so in order to gain quicker boot. So calculating CRC of big image can take few minutes, and you sit in a car, you want to drive, you don't want to sit waiting for system to boot up. Also, no advanced features like secure boot or file system encryptions are supported. And this is part that we took from developer sites and their recommendation to eliminate a bit of security in order to gain better responsiveness of the system. So as I mentioned, these devices that we have tested are OEM manufacturers. So it is not related to a specific car model that we were using for testing. We could test it in any car practically. And we have discovered that these devices are actually deployed in a lot of different brands. When we have when we have done everything, we have grabbed the image of the operating system, and we have found strings related to different car manufacturers which are using the same device. So they have one basic device, and then they do some customization in some specific cases and by specific requirements of specific manufacturers, but that's it. So underneath, they're all the same or similar. And as I mentioned, so this is OEM car manufacturer will not support this. They rely on original equipment manufacturer to support this, and it can take time to fix any issues in firmware. So I'm not sure if and how long it took them to fix all the issues that we have found, but we hope they finished after a year or more when we have reported all of this. And in the end, it comes from car manufacturers. So car manufacturers need to be the driving force that make OEMs fix the problems. So if they are doing that or not, that's up to them. But if something bad happens, it will be on both sides. So what is the attack surface? So when we disassembled and started analyzing devices, we discovered that there are a lot of interesting features that can be used to access these devices. So first idea was we are not going to dismantle the whole car. So that was sane idea because we couldn't return it back. We are security expert, not car mechanics, so we don't want to venture into that part. So we started evaluating what are exposed interfaces, and first and most interesting are USB and CD ports. So they support a lot of different file formats and a lot of different functions, so you can just connect USB flash drive, but can you connect keyboard to it? What will happen if you do it? So we also saw that upgrade procedure for the firmware of device actually can be done by customer and user, but you need to go to internet, download, update image, prepare a flash device, put flash device in USB port, and then do a little bit of complex setup in order to start the update process. So it's not easy and trivial. Then we saw that there are a lot of different radios available, like Bluetooth, Wi-Fi. There is standard FM, there is GPS, of course, positioning. So if you were here last year, I gave a long talk about radio assessment and their applicability to automotive industry, so that would be interesting reading for this. So what we did is we did fuzz over radio waves, we did interception of radio communication in order to see what is exchanged and how devices are communicating. And then we proceed into dismantling a little bit more of cars. So this was first without touching anything, so the device was fully mounted inside the dash. After that, we started removing plastic from the dash and start removing device outside of car to see what is inside. So on this picture, you can see device outside of the chassis. So we just pulled PCB out and started analyzing what is inside. And we found a lot of interesting stuff, like EPROM SD card, we found I2C protocol, we found something that is JTAG ports. So we have found a lot of interesting stuff that provides attacker opportunity to do something with device that is not actually planned by the car manufacturer. So after we have disassembled everything, removed devices from the car, I took pity on Ben, because you can see he's really, really cold in a cramped car with me, and I'm not a small person, and we have a lot of equipment, so it was really difficult to be working in cold, outside, and relying on pity of strangers to give us something warm, or a little bit of gasoline to fill the car so we don't freeze to death. So we decided to consider if we can move testing out of the car and into the lab. And not just testing of the passive devices, but to have fully working device in the lab without actually putting car inside the lab, because that would be a bit of problem. Our entrance are made just for people, not for cars. So we would need to really disassemble car and reassemble it back in the lab in order to put it inside. So we started first by analyzing connectivities that are provided by car to device, and to see how device is behaving in normal operation. So we first and most thing, we know that all devices need to be powered. So they need plus 12 volts and chassis in order to work. And since everything is customized, we need to discover where these connectivities are provided and how. Also, this device seems to be integrated into the CAN bus of the car. So as I mentioned, CAN bus is the very important interface because a lot of devices can communicate over it. So we have two CAN buses in the car usually. One is called slow bus, one is called speed bus. Speed bus is used to communicate between the motor control unit and other control units that are critical for car operation. And slow speed bus is used inside your cabin to provide you entertainment and comfort. So they operate AC device, they are operating movie players, so stuff like that. So this device was connected, but during the checking we couldn't determine if this device is actually using anything from CAN bus. So, but to be on safe side, we decided to try and to sniff CAN bus in order to see if device is actually using. So first thing that we do, we remove device from CAN bus and use different tools to connect to this. So I'm showing here a little bit of my favorite tools. We have a little bit more professional tools, but the problem with professional tools, they are made by somebody and have specific purpose. And when you are working with hardware, you need to be able to deploy your own tools because it's necessary. As I mentioned, car manufacturers are actually using proprietary stuff. So if you use run-of-the-mill tools, you might have problem actually accomplishing anything. So I like this board. It is based on STM32, and it is really versatile. It's very cheap. It's cheaper than Arduino on the internet. So you can buy it for cheap and easily programmed. And if you add it to the CAN bus shield that is available for Arduino, you can do a lot. Actually, this microcontroller that is deployed supports both USB and CAN bus. And I was so happy. I was hoping that I can make tools just adding the transceiver and it would be it. But unfortunately, due to some unfortunate decisions made by STM, it is not possible to use both features at the same time. They share some part of memory and it is impossible. So I have also proper CAN bus sniffer here. So what we did, we sniffed CAN bus and we saw what car normally is using, which messages are normally seen on this bus. Then we connect the device and start sniffing again. And activating different features, we couldn't find any difference. So in the end, we decided, yes, we can provide CAN bus. We will emulate everything that we have sniffed, but it is probably not used by the device. And actually, only a single feature that supports this is car reads fuel consumption, but it doesn't work for some reason. So we will go into more details about it. So even if it is provided, so there is a hardware, there is a software supporting CAN communication, device is not using it because it is a little bit outdated. So we moved everything into the lab, provided power supply and CAN bus and we started working a little bit more, exploring what we can find. And first thing that we know, that we already knew before, is that this device is using, it doesn't have its own internet connection, but you need to provide it by joining this device to your mobile phone. So you can do it in two different ways, either via Bluetooth or Wi-Fi. So low-end devices use Bluetooth, high-end devices are using Wi-Fi. So with Wi-Fi, it was simple. So we used standard tools to set up intercepting. We created our own rough access point and associated device with this access point, and it was easy to gain access to traffic, which was sent between the device and the internet. It was a little bit more difficult with Bluetooth because it was not using just normal private area network connectivity over Bluetooth, but it first required to establish a hands-free protocol. So it will try if he can do hands-free, and only if it is successful, then it will initiate networking. So we needed to emulate this part because no tool were supporting this. So we developed small Python tool that implemented this protocol. Of course, we needed to implement only important parts that were necessary for this device to operate. And as a result, we were able to emulate and capture traffic also via Bluetooth. So that's all for me. We go now to Ben.
So Vladan has been very quick on the Bluetooth part, but it was taking us a lot of time to figure out why the device didn't want to communicate with the backend system without the hands-free protocol. So the hands-free protocol, if I can go to the slide before, is mainly relying on AT commands. So if you have been playing with modems, something like 20 years ago, you've been using the AT commands to configure your modem. The hands-free protocol is exactly the same. It's built on top of AT commands. So it's just a serial line and commands exchange between the Bluetooth device and the phone. So for example, here you can see a screenshot, just the device asking for the mobile carrier network name. So now we are going to discuss about the existing attacks and why they don't work anymore on the devices we have tested. A couple of years ago, I think it's 2014, in Black Cat and DEF CON, there has been some talks regarding the Jeep cars which were hacked remotely. The Jeep cars, you remember Vladan told you that the devices were OEM devices. The Jeep cars use similar OEM devices. When I say similar, it's the similar hardware and similar software. The Jeep were vulnerable because it was possible to get access to them remotely using Telnet. And when you sit on the device with Telnet, you are able to jump on the D-bus with TCP and then able to communicate with various services of the device. And finally, abuse the firmware upgrade process to have permanent access to the device. So in our case, Vladan told you that we could communicate with the device using both Wi-Fi and Bluetooth. So this is the very first step to compromise the device. Unfortunately for us, all the other vulnerabilities have been fixed. So D-bus TCP is not accessible anymore, Telnet is not accessible anymore, and we couldn't have used the firmware upgrade procedure because they are now using a secure signed firmware validation. So what could we do? One of the attack angles we have chosen is attacking the third-party applications. The device we've been testing did support an app store to install third-party application. So it can be like your phone, you have the app store on iOS or Android is exactly the same, excepting that there are much less applications offered and all the applications are controlled by the car manufacturer. So you as a hacker, you cannot get access to the software development kit and you cannot add your own application. So the very first step was to intercept the communication between the App Store application and the backend systems. We figured out that it was using HTTPS, which is good. Unfortunately, we also discovered that the encryption is totally broken, and if you try to intercept the HTTPS communication and sign it with your own self-signed certificate, it will work and will not display any warning to the end user, which is a small problem. The second thing we discover is the communication with the backend system is done using XML messages, so very similar to SOAP web services requests. So it's using XML messages with get and post HTTP request. The first attack we conducting is abusing the statuses of the application. When the device, the App Store, asks for the list of available application, the list of application is returned with a status which is either buy, install, or installed, which means if you have buy, the device will show buy and you will have to pay for the application. But if the status is just installed, you can click on the install button and get the app for free. So the logic control is done at the client side, so in your car, and not on the backend system in the server side. So this is a major finding which reminds us to the first mobile applications almost 10 years ago now. The second thing is, so the first thing is we could get app for free. So what next? Here you can see the XML document that we have just changed the buy and replaced by install to be able to install pay application for free. So next we wanted to reverse the application that we found on the server. So each application can be retrieved because when you get the software catalog from the backend system, it provides you with the URL and it's system exposed on the internet. It's not using a VPN, there is no authentication, nothing. So if you have the URL, you can download the mobile application packages. Each package is a zip archive, so you download them. And in the zip you will find two things. So you will find a jar, which is Java archive, and a signature file. The signature file is a bit of problematic for us because we figure out that it is a RSA signature. So it is based on public and private key architecture, and we could not break it. We tried to resign it with random keys and it didn't work. Fortunately, the Java source code was not obfuscated, but the Java bytecode itself was signed. So here we are facing a double level of signature systems. First of all, a file signature, and the second thing is code signature. So does it mean it was game over and we couldn't attack here? No. So we started with decompiling the source code of the App Store itself because the App Store package was available as an update on the remote server. The first thing which I mentioned is the source code was not obfuscated. Long story short, here is the installation process. So the device starts and checks if the status is installed. If the status is not installed, it exists. The second thing is it starts downloading the zip archive. And then it tries to extract the zip archive to a temporary area. Only after that, it will check if the jar file is signed properly with the file hash signature. And if the signature matches, then it will install the application on the device permanently. So before checking the signature, this is very important and a key here, before doing the installation, the device has to download the file and extract it to a temporary area, even before checking the signature. And this is one of the vulnerabilities we will exploit here. So this is just 2 lines of the code we reversed, and if you are a good software hacker here, you will figure out that there is a hard-coded temporary path, and then it is concatenating what we call the zip entry, so the file name here, with a slash. So what should come to your mind is file injection and directory traversal vulnerability. So what happens if we manage, by chance, to change the name here by something like ... something else? So if you try to do this on your laptop and use unzip, winzip, or 7-zip, it will not work. It will write something like removing a leading trail or whatever message. But what happens with this dirty Java code? Well, guess what? It works. So what we did is, with Python, we created a crafted zip archive, which contains a lot of dot dot slash because we don't know where we are in the file system. So we put a lot of them. The number doesn't matter. Well, it needs to be sufficient. And then, because we don't have access to the device, if we want to check if we are able to write something somewhere, we need to write something in a place we can check. So here, the only thing we add is if we attach a USB key to the device. And you can attach a USB key because you can use your USB key to play MP3 on the system. So just put a USB key. On QNX, the USB key are automatically mounted in /fs/USB0. So here, if this zip archive is accepted, it will create an empty file on the USB stick. So we did this, we installed the archive and it got installed. So we could find our file here on the USB stick. So what is the next thing to do? We are able to write content somewhere, but what we want to do is being able to execute content, not to only copy files. Vladan mentioned that a lot of file systems are mounted as read-only. This is because of embedded file system, and this is a very common finding in mobile environment. So what we need to do is to find a location where we are able to write on the device. We know that there is a place for sure which is writable. It is the place where the third-party applications are stored, because when you install the application gets stored on the device. So we needed to find this location and be able to put something in this location. Then the next thing to do is to execute it. So there are two problems here that we need to solve. Where are the apps installed on the file system? And the second thing is how to recompile a Java application without the correct SDK or API. As I mentioned, the application are using a custom SDK and application API, and we were not provided with this, and we couldn't find anything on the internet. So we needed to patch the Java application to execute our content. So what about Java backdooring? Most of you have probably been playing with a debugger like Immunity or Holy, and I've been patching the software to execute malicious instruction or to backdoor them. Is it possible to do the same with Java applications? The answer is yes, definitely. But there is very little talks about that on the internet. So what is the Java bytecode? Java bytecode is Java source code which has been compiled and which get executed by the JRE, which is Java Runtime Environment. It is very similar to assembly code, but working for a specific CPU, which is the Java Virtual Machine, the runtime environment. So if we can backdoor a portable executable or ELF file, it is possible to do the same with a Java bytecode. Remember, here, in our case, we found that the jar file is signed, which means that if we change the bytecode, the signature of the source code will be different, and normally the Java runtime environment should refuse to run our malicious code. So if you are doing this on a PC, you will get an error message like the signature is not good and the file will not be executed by the runtime environment. So before starting to do complex stuff, we decided just to change in the application package a PNG icon. The PNG icon is signed like the rest of the content of the jar file. So we changed the PNG icon of a software, and we tried to start the patched application, which didn't work. The jar signature was rejected, but the Java virtual machine. So does it mean game over? Still not. So how does it work, the Java signature of archives? It's basically a key and then the digest of all the files contained in the archive. But what happens if we just remove in the manifest the digest of files and the key here? It works. Because there is a failure here. Here is what is implemented. They consider that there will always be a signature in the archive. So what they do is they check if the signature is good, it accepts. If it's not good, it rejects. But they have not considered the option of what happens if there is no signature. So no signature, no problem. It runs without any warning. So now we have to prepare a payload. So the step is to create a payload in Java, so basically just execute a process. Here we decided to execute a script that we hosted on our USB stick, so that doing this prevents us to every time, because we are telling you the story in 1 hour, but it took several weeks because it is blind attack, so you don't have any error message, not nothing. So it takes your time, you compile, recompile, retest, reinstall, and it's taking a lot of time. So what we decided here is just to execute a script on the USB key we can easily change with the computer without having to recompile and reinstall all the time. So we created this payload. We copy the compiled payload to the jar file. And then we have to hijack the execution flow of the application to redirect it to our payload. What's important to do here is to use the correct compiler version when you are doing that, because if you compile it, for example, for Java 1.6 and the device just uses 1.4, then it will not work. So modifying the bytecode is as simple as adding 3 instructions. So what's the most important here is invoke static with your payload. So if you put it in the start instruction of the application, your payload will be executed before anything else. And it works. So now every time we are starting the application on the infotainment system, the script which is located on the USB stick gets executed. So what we should do here, the next thing is we figure out we were able to execute command. So we were able, for example, to copy files from the file system and do offline reverse engineering. But what we wanted to do is to get interactive access to the device. So there was 2 solutions for that. You cannot, as we mentioned, you cannot generate a meta-operator for QNX because it's a specific CPU, it's a specific operating system, so it will not work, unfortunately. So what we had to do is to be able to start Telnet or to start QCon, which is the QNX debugging daemon. But QCon was not in the build because following the recommendation of QNX, when you are building your production image firmware, you remove unnecessary daemon and you remove QNX. So what we did basically is very stupid, but we were looking for some other QNX images on the web, and we figure out that the CPU used here has the same instruction set as a Raspberry Pi. And we find out that some people had compiled QNX for support on Raspberry Pi. So in a QNX image for Raspberry Pi, we could find a QCon daemon, and we were very lucky. Copying this daemon to the system did work, and we were able to start QCon and then get permanent access to the device. So now maintaining access and post-exploitation. So maintaining access means that we have our daemons restarting automatically when we are restarting the device. So it can be Telnet or QCon. So for the story, we have cracked the root password of the device. This password is generated on the build. So for every different build level, there are different root password. So it's not using a car or automotive, but it's just a random one. But luckily, they are using Descript, which means the password can only be 8 characters. So the password could be cracked within few hours, and a powerful system with GPU. We were able to crack the root password to get permanent access in Telnet if we are able to start Telnet. So we had to find a script or an executable which resides on a partition we can write, so mounted as read-write, to be executed at the next boot. So we investigate and we finally found one, so we could hijack the boot process of the device itself to start our daemons at the system restart. Here you need to be very careful because there is no reset to factory to restore the file system. So if you mess the boot process of your device, you just end up with a brick. An expensive brick, but a brick. Here, the post-exploitation of the device, because now we have full control of the device, so we started to play with the device itself and see what funny things we can do. What we find out is most user data are stored in SQLite database, like any Android phone. So if you imagine that you can do the same attack on a rental car, you will be able to access all the data on the phones of the previous drivers of the car. So you will get the phone books, and if the user is using an Android phone, you will find as well the SMS messages, which can be fun. You can obviously find the API, endpoint, and keys for the remote services. So the device has, for example, services for traffic information. You can find the passwords and the credentials to use those remote services. You can play with the graphics, so you can change the look and feel of your device. And you can find various services which are connecting to the D-bus. One of them, which is very funny, is the TTS. So if you send a message to the TTS service, the car will start to be talking to the driver through the speakerphones. So it can be very scary if you attack the car of somebody and say, "Hello, I own your car." So most of the actions, so the services which are connecting to the D-bus, are scripted in Lua. So here they are using compiled Lua, so you cannot have direct access to the source code, and they are using non-traditional Lua compiler. So we couldn't decompile immediately. What we figure out is if we reuse some decompiler from GitHub and we patch them to ignore the checksum or the magic number checking, with a version 5.1 or 5.2 we were able to decompile the Lua and recover the source code, which was very fun. And then we finally re-enabled D-bus over TCP, which means that we can interact with the D-bus remotely without being sit on the car, which is very fun because, as I mentioned, you can play with some services like text-to-speak, or you can change the location on the D-bus, so the navigation system will not work. It will think it is in another place. So the Grail. The Holy Grail is the CAN bus. Because if you get access to the CAN bus, you get access to critical systems of the car. So the braking system, light, management of the temperature, everything. Unfortunately for us, the systems we have been testing were not using the CAN bus. Although the CAN bus is connecting to the device, the system could not use the CAN bus because it didn't have the required piece of code and the proper CAN bus transceiver. So instead of that, because the device was pretty crap, it was using a kind of converter, and it was talking with the converter, but the converter itself was talking with the CAN bus. So we could only recover a limited set of information from this transceiver, such as the fuel consumption or whatever, but we could not get access to the full CAN bus, which was really frustrating. So the important part here is it was not a security countermeasure, it was just a poor device design. So finally, I'll go quickly because we don't have a lot of time, but the hardware attack, because we have been talking about the software side, but there is also the hardware side. So one of the very interesting things we noticed on the device board is this. It looks like debug ports. So what we did is we had attached our favorite clamps here, and we started to use the logic analyzer. So we were quickly able to identify a console. So here you have the full boot process of the QNX, but as we mentioned, QNX is not Linux, so you cannot edit, for example, the group command line to be executed to boot in single user mode. So the device is booting and then prompting for a password. And as I mentioned, the root password is changed on every build, so you cannot find it unless you manage to extract using the previous technique the shadow file. So the serial console requires authentication. What we found out, however, is there is a FRAM. So FRAM is a very small memory, so in our case it was 8 kilobytes, and we figured out that this chip was containing the persistent information regarding this device. So for example, the MAC address, the serial number, and various settings. Because when you are installing the software on the device, the serial number cannot be the same on every device. So device-specific information are stored here in this FRAM. Another interesting thing is, if you remember, Vladan has introduced the boot process of QNX, and the very, very first stage of the boot process is the IPL, Initial Program Loader. And the IPL is in this small FRAM chip. Why? because the device, the SoC, is not able to communicate with a large flash by itself. So it has to use a driver, and this is exactly what is doing the IPL. It's just loading the driver to be able to load the rest of the file system from a large memory chip. So here the work is still in progress, but what we want to do is to hijack the IPL boot process to be able to get access and bypassing the root logging and to be able to land in a single user mode. So what is the takeaway of these conferences? The main message here, what we want to say is, if you are a good software and system hacker, don't be afraid of trying to hack the hardware, because as we just demonstrated, here we managed to compromise hardware system using software exploitation. Thank you for attending our conference, and if you have questions.
So, any questions?
Hi. You mentioned at the beginning of your presentation that the EBD port, right, is mandatory.
OBD, yes.
Yeah, the OBD. Why do you think that that's the case? I mean, it's to access the components of the system, the car. Sounds to me like something that's nice to have. Why is it legally binding?
It is required by law. So, first idea is to enable updating software on computers. Second is to control emissions. So, there are aftermarket devices which requires this access, and the most important part is to enable diagnostics. So, OBD is diagnostics part. In theory, you shouldn't be able to run anything dangerous because, as I mentioned, we have multiple buses in the car, and there should be something that is called gateway device, which is acting as a filter. So when you connect to OBD, this gateway device should filter the requests that are coming from OBD port into the other system. So it should prevent, it's like proxy, web filtering proxy. It will filter some dangerous URL in order to keep your traffic clean. So idea is that this OBD should not be dangerous, and that this gateway device should filter all dangerous requests. But what we saw in practice is that these gateways sometimes are not done properly, and there are possibilities to bypass them. Also, there is a feature that enables upgrading ECU software, and it is normally done by utilizing challenge response authentication. But if you're persistent enough, you might be able to crack this challenge response process, because, as I mentioned, automotive manufacturers like to use proprietary stuff that usually they invented, which are not properly designed and properly tested, and leaves a lot to be desired from security perspective. So yes, OBD can be dangerous. It was not envisioned to be dangerous.
Yeah. Okay. Thank you.
Anybody else?
Hello, thank you for this great presentation. I'm sorry I missed the first part, so maybe you mentioned this. I just want to ask you how much time did this specific hack take you, and how did you find that time? Is that your daily job or whatever? How do you do that?
It's part of our daily job. So we are X4Threat, we are IBM team of hackers, so we are doing this as a part of project, a research project, but this is part of our daily work. And in these specific cases, it took about 3 months from beginning to end. So of the first phase. So we consider this to be work in progress. The harder you always want to do more, and you have abilities to do more. So it's just a question of finding enough time to do it.
Cool. How many of you are in the team?
Our team is big, but in this specific case, it was just 2 of us
Just 2
that
of you.
delivered the work. Yeah.
Cool, thanks.
Hi, thanks all for the brilliant presentation and everything. I know you spoke about the same chip being used by multiple manufacturers and everything, but have you encountered in your research that, let's say, car manufacturing corporations, for let's say Volkswagen, Audi groupation, or GM, did you saw any identical, let's say, circuits being used between, let's say, GM and VAG?
We've seen the same hardware, but more interesting, in the firmware, we found different strings. So there is a setting like manufacturer number, and based on that, it will has different string with the name of the manufacturer.
Absolutely identical hardware.
Some pieces of software are absolutely identical, and the hardware is definitely.
So they build one hardware platform, and then they build the standard software part, and there is only a small user application layer that is different between different manufacturers, let me put it that way.
I would like to talk to you about this later.
Sure, we will be in lounge, so
Not to waste anyone's time anymore.
with beers we can talk a lot. More beers,
Awesome.
more talk. Behind you.
Hi, just short question. You mentioned that manufacturers did change something after your findings, so I maybe missed what was changed after your findings.
We still don't know, so we are waiting to do the retest of new version of devices to see how this actually impacted. But during this, we have been working with car manufacturer a lot, help them understand security requirements, help them define security framework model that they need to insist when they are procuring this, because they do not manufacture these devices on their own. They're buying them from OEM manufacturers, and we help them develop this framework so that they can go, oh, we want to buy this kind of device from you. Can you please implement these security requirements?
Yeah, this is something which is very interesting is some car manufacturer, I cannot say all of them because I don't know all of them, but some of them don't have the development capability inside. So they just go to the OEM provider and say, okay, I want this, I want this. There might be a feature catalog and they might cross some ticks like I want this feature, I want this feature. We don't know, but they don't have the capability to rebuild the firmware inside. Another interesting thing is I figure out that in another car, there was the same hardware, but the security, the software security was much better. And the car was, for example, using an IPsec tunnel over the Wi-Fi or the Bluetooth so that you cannot intercept anything. So here it reveals that it's also a matter of willingness from the car manufacturer to pay for the security features or not.
Thank you.
Anybody else? We like to hear your voices. We talked to you for an hour.
Sure. Thank you very much.
Thank you.